Welcome to your first semester of zoology. Today, we are diving into a topic that sounds like it belongs in a horror movie, but is actually a very real and fascinating biological process. Imagine leaving fresh meat on a counter, only to find it swarming with maggots hours later. Now imagine that happening to living tissue. This is the reality of myiasis, a critical topic in the study of insect vectors and diseases. Let us begin our exploration. To understand what myiasis is, we first need to think about the basic life cycle of a fly. You have likely seen flies swarming around decaying food. They lay their eggs there, and those eggs hatch into tiny worm-like creatures called maggots, which consume the matter to grow. But in the case of myiasis, the flies do not choose decaying food. Instead, they choose a living human or animal. The larvae literally move into the host's body, feeding on their living tissues. It is a destructive and invasive process, but biologically, it is a highly evolved survival strategy. Now that we have a general idea of the condition, let us look at its formal scientific definition. In medical and veterinary entomology, myiasis is strictly defined as the infestation of live humans or vertebrate animals by the larvae of flies. Importantly, these flies must belong to the order Diptera, which are the true flies. During their developmental period, these maggots sustain themselves by feeding on the host. They might consume dead tissue within a wound, actively destroy living tissue, drink liquid body substances, or even steal the host's ingested food. This definition sets the boundary for what we classify as myiasis. Building on that definition, doctors and veterinarians need ways to categorize these infestations to treat them effectively. One primary way to classify myiasis is by the anatomical site that is affected. If the maggots burrow into the skin or an open wound, we call it dermal myiasis. If the larvae are swallowed and survive in the digestive system, it is known as intestinal myiasis. And if the flies lay eggs in or around the nose, leading to an infestation of the nasal cavities, it is termed nasal myiasis. Knowing the location helps predict the potential complications. Beyond just where the maggots are located, we must also classify myiasis based on the biological relationship between the fly and the host. This brings us to two crucial terms. The first is obligatory myiasis. In this case, the fly species absolutely requires a living host to complete its life cycle. Without living tissue, the larvae will die. The second is facultative myiasis. These flies normally lay their eggs in decaying organic matter, like a carcass. However, if they find an untreated wound on a living animal, they will take advantage of it and infest the living tissue. This distinction is vital for identifying the fly species. Understanding these classifications leads us to ask, why is this so important? The answer lies in the massive medical impact myiasis has, especially in tropical and subtropical regions of the world. In human medicine, an infestation is not just uncomfortable, it causes severe pain and massive tissue destruction, as the larvae literally eat the host alive. Furthermore, the open lesions they create are perfect entry points for secondary bacterial infections. In extreme cases, if the larvae manage to invade deep tissues or critical organs like the brain, the condition can absolutely be fatal. It is a serious medical emergency. While the human toll is severe, the impact on agriculture and veterinary medicine is equally staggering. Every single year, myiasis causes billions of dollars in economic losses worldwide. When livestock, such as cattle or sheep, become infested, the stress and tissue damage lead to drastically reduced milk and meat production. Additionally, As the larvae burrow through the skin, they permanently ruin the animal's hide, destroying its commercial value. If left untreated, these infestations frequently lead to the death of the animal. This is why farmers and scientists are constantly working on control strategies, like releasing sterile male flies or developing better insecticidal dressings. To truly grasp how quickly this tissue destruction occurs, biologists rely on mathematical models. Because larvae feed continuously, their mass increases rapidly, which directly correlates to how much host tissue they have consumed. We model this using the standard exponential growth formula. M of t equals m0 times e to the power of r times t. In this equation, m of t represents the total mass of the larvae at a given time, usually measured in milligrams. m0 is the initial mass of the larvae right after they hatch. The constant e is the base of the natural logarithm. The variable r is the relative growth rate, which increases with warmer temperatures or more aggressive fly species. Finally, t is the time elapsed in days. If r increases, the mass skyrockets, meaning the host's tissue is destroyed much faster. Let us see this formula in action with a concrete example. Imagine a sheep with a small wound that becomes infested with blowfly larvae, causing facultative myiasis. We are given that the initial mass of the newly hatched larvae is 5 milligrams. The growth rate for this species in a warm environment is 0.6 per day, and we want to find the mass after 4 days. We substitute these values into our exponential growth equation. First, we multiply the growth rate of 0.6 by the 4 days, giving an exponent of 2.4. Using a calculator, e to the power of 2.4 is approximately 11.02. Multiplying this by the initial 5 milligrams gives us 55.1 milligrams. Physically, this means the maggots have multiplied their mass by more than 11 days in just 4 days, consuming a significant amount of the sheep's flesh. Now that we have calculated the damage to a single animal, we must look at the herd level. Epidemiologists and farmers need to understand how fast the disease is spreading through a population to know when to intervene. They do this by calculating the incidence rate. The formula for incidence rate, which we will call I, is the number of new cases, C, divided by the total animal time at risk, T. Animal time is simply the number of animals multiplied by the number of days they were exposed to the flies. Finally, we multiply the entire fraction by 1,000. This standardization is crucial because it allows us to express the rate as cases per 1,000 cattle days, making it easy to compare different herds or different seasons, regardless of the actual herd size. Let us apply this incidence rate formula to a real-world scenario. A farmer has a herd of 500 cattle. During a 30-day peak summer period, 45 new cattle develop painful skin lesions caused by botfly larvae. First, we calculate the total animal time by multiplying the 500 cattle by the 30 days of exposure, which gives us 15,000 cattle days. Next, we take the 45 new cases and divide them by those 15,000 cattle days, yielding 0.003. Finally, we multiply by 1,000 to standardize the metric. The result is 3 cases per 1,000 cattle days. If the farmer's threshold for emergency chemical spraying is 2 cases per 1,000 cattle days, this calculation scientifically proves that immediate intervention is necessary to prevent further economic loss. To fully understand how to break this chain of infection, we must visualize the life cycle of the flies responsible for myiasis. Look at the diagram on your screen. The cycle begins with the adult fly, which lays its eggs. Sometimes these eggs are transferred via a vector, like a mosquito, or laid directly on the host. The eggs hatch into larvae, which burrow into the host's tissue, creating a painful, swollen lesion known as a warble, clearly visible in the skin cross-section. Once the maggot matures, it drops out of the host and burrows into the soil to pupate. Finally, an adult fly emerges from the pupa in the soil, and the destructive cycle begins all over again. We have covered a lot of ground today, so let us review the key takeaways. First, myiasis is a severe biological phenomenon where dipteran fly larvae infest and feed on the living tissues of vertebrate hosts. We learned that this can be an obligatory process, necessary for the fly's survival, or a facultative one, taking advantage of existing wounds. Furthermore, we saw how mathematical models, like exponential growth, allow us to quantify the terrifying speed of tissue damage. Finally, calculating incidence rates helps epidemiologists and farmers track the spread and implement critical pest management strategies. Mastering these concepts is your first step toward developing effective medical and veterinary treatments.